There are several possible causes for electrical equipment damage in a commercial setting, even when breakers do not trip. These include power surges, ground faults, aging or faulty breakers, and circuit overloads. Overvoltages can damage electrical equipment, even if breakers don't trip. Ground faults can create voltage spikes that bypass breakers. Breakers can fail to trip even when overloads occur. High current draw can damage equipment even if breakers don't trip immediately. Panel surge protectors can help mitigate power surges by diverting excess voltage to the ground. However, they are not a guaranteed solution for all equipment damage. Surge protectors only provide protection against voltage spikes, not ground faults or circuit overloads. They should be properly sized and installed to handle the specific voltage and current requirements of the equipment they protect. To address the problem effectively, firstly, identify the root cause through thorough testing to determine the cause of the equipment damage. This may involve measuring voltage levels, checking ground connections, and analyzing breaker performance. Secondly, upgrade or replace breakers. If breakers are faulty or outdated, replace them with reliable and modern models. Thirdly, increase circuit capacity. If circuits are overloaded, consider upgrading the panel or adding additional circuits to distribute the load more evenly. Fourthly, install surge protectors. While surge protectors may not solve all problems, they can provide additional protection against voltage spikes. Ensure they are properly sized and installed. Fifthly, consider a voltage regulator. A voltage regulator can help stabilize voltage levels and reduce the risk of surges. Lastly, conduct regular maintenance. Perform regular inspections and maintenance on the electrical system, including breakers, wiring, and surge protectors to ensure they are functioning properly. Consider also equipment age and condition because older equipment may be more susceptible to damage from power fluctuations. Consider environmental factors too because extreme temperatures or humidity can affect electrical equipment performance. It's important to ensure that heavy equipment is not operated simultaneously to avoid overloads. When dealing with electrical issues, it is crucial to adopt a systematic approach to accurately diagnose the problem and implement effective solutions. Firstly, it is imperative to perform a comprehensive visual inspection of the electrical panels and connected equipment. Look for any signs of damage such as discoloration, burning, or loose connections. Check the panel for proper labeling and ensure that all breakers are correctly identified. Secondly, utilize a multimeter to measure voltage levels at various points in the electrical system. This will help identify any voltage drops or imbalances that could be contributing to equipment malfunction. Compare the measured voltage to the expected voltage and investigate any discrepancies. Thirdly, conduct a thorough ground fault test to identify any unintended paths to ground. This can be done using a ground fault locator or by performing a continuity test between the equipment grounding conductor and other grounded surfaces. Fourthly, evaluate the condition and functionality of the circuit breakers. Check for any signs of wear or damage and test the breakers to ensure they trip properly under overload conditions. Replace any faulty or outdated breakers with new ones that meet current safety standards. Fifthly, assess the overall load on the electrical circuits. Use an ammeter to measure the current draw of each connected device and compare it to the circuit's rated capacity. If the circuit is overloaded, consider redistributing the load to other circuits or upgrading the panel to increase capacity. Sixthly, install appropriately sized surge protectors at the main electrical panel and at individual equipment locations. Surge protectors help to divert excess voltage caused by power surges, protecting sensitive electronic devices from damage. Seventhly, consider the installation of a voltage regulator to stabilize voltage levels and reduce the risk of voltage fluctuations. Voltage regulators help to maintain a consistent voltage supply, preventing damage to equipment caused by over or under voltage conditions. Eighthly, implement a regular maintenance program for the electrical system. This should include periodic inspections, testing, and cleaning of electrical panels, breakers, and wiring. Proactive maintenance can help identify potential problems before they lead to equipment failure. Lastly, ensure that all electrical work is performed by qualified and licensed electricians who are familiar with local codes and regulations. Proper installation and maintenance are critical to ensuring the safety and reliability of the electrical system. Power surges are transient overvoltage events that can damage or destroy sensitive electronic equipment. These surges can originate from various sources, including lightning strikes, utility grid switching, and internal electrical events within a building. Understanding the nature of power surges and the protective measures available is essential for safeguarding electrical systems. Power surges typically occur in the form of short-duration, high-voltage spikes that exceed the normal operating voltage of electrical equipment. These spikes can induce excessive current flow, leading to overheating, insulation breakdown, and component failure. Surge protection devices, also known as surge suppressors, are designed to mitigate the effects of power surges by diverting excess voltage to the ground. These devices contain components such as metal oxide varistors, silicon avalanche diodes, and gas discharge tubes that clamp the voltage to a safe level, protecting connected equipment from damage. There are several types of surge protection devices available, each designed for specific applications. Firstly, whole-house surge protectors are installed at the main electrical panel to protect the entire electrical system from external surges. Secondly, point-of-use surge protectors are plugged into individual outlets to protect specific electronic devices. Thirdly, surge protection strips provide multiple outlets with surge protection, making them suitable for protecting multiple devices in a single location. Fourthly, dedicated surge protectors are designed for specific types of equipment, such as telephone lines, coaxial cables, and Ethernet connections. When selecting surge protection devices, it is important to consider several factors. Firstly, surge current capacity is the maximum amount of surge current that the device can withstand without failing. Secondly, voltage protection rating is the maximum voltage that the device will allow to pass through to connected equipment. Thirdly, response time is the speed at which the device can react to a surge event. Fourthly, clamping voltage is the voltage level at which the device begins to divert excess voltage to the ground. Fifthly, let-through voltage is the voltage level that the device allows to pass through to connected equipment during a surge event. Sixthly, UL 1449 listing is a safety standard that ensures the device meets certain performance and safety requirements. In addition to surge protection devices, there are other measures that can be taken to reduce the risk of power surge damage. Firstly, proper grounding of the electrical system is essential for providing a safe path for surge currents to flow to the ground. Secondly, avoiding the use of extension cords and power strips can help reduce the risk of voltage drops and overheating. Thirdly, unplugging electronic devices during thunderstorms can protect them from lightning strikes. Fourthly, installing lightning rods on buildings can help to divert lightning strikes away from the electrical system. Ground faults are unintentional electrical connections between a live conductor and ground. These faults could occur due to damaged insulation, loose connections, or equipment malfunctions. Ground faults can pose a significant safety hazard, as they can cause electric shock and fire. Ground fault circuit interrupters are designed to detect ground faults and quickly energize the circuit, preventing injury or damage. Ground fault circuit interrupters, also known as ground fault interrupters, are electronic devices that monitor the current balance between the hot and neutral conductors in an electrical circuit. If a ground fault occurs, the current flow in the hot and neutral conductors becomes unbalanced. The ground fault circuit interrupter detects this imbalance and trips the circuit, cutting off the power supply. Ground fault circuit interrupters are typically installed in areas where there is a high risk of water exposure, such as bathrooms, kitchens, and outdoor locations. There are several types of ground fault circuit interrupters available, including receptacle-type ground fault circuit interrupters, circuit breaker-type ground fault circuit interrupters, and portable ground fault circuit interrupters. Receptacle-type ground fault circuit interrupters are installed in place of standard electrical outlets and provide ground fault protection for devices plugged into the receptacle. Circuit breaker-type ground fault circuit interrupters are installed in the electrical panel and provide ground fault protection for the entire circuit. Portable ground fault circuit interrupters are designed for temporary use and can be plugged into standard electrical outlets to provide ground fault protection for tools and equipment. When installing ground fault circuit interrupters, it is important to follow the manufacturer's instructions and local electrical codes. Ground fault circuit interrupters should be tested regularly to ensure they are functioning properly. To test a ground fault circuit interrupter, press the test button on the device. The ground fault circuit interrupter should trip, cutting off the power supply. If the ground fault circuit interrupter does not trip, it should be replaced. Aging or faulty circuit breakers can pose a significant safety risk. Circuit breakers are designed to protect electrical circuits from overloads and short circuits by interrupting the flow of current when a fault occurs. Over time, circuit breakers can become worn or damaged, compromising their ability to function properly. There are several factors that can contribute to the aging or failure of circuit breakers. Firstly, repeated tripping can cause wear and tear on the internal components of the breaker. Secondly, exposure to moisture or corrosion can damage the breaker's contacts and mechanisms. Thirdly, overheating can cause the breaker's insulation to break down. Fourthly, physical damage can compromise the breaker's structural integrity. Signs of aging or faulty circuit breakers include difficulty tripping, failure to trip under overload conditions, discoloration or burning, loose connections, and unusual noises. If a circuit breaker exhibits any of these signs, it should be inspected and replaced if necessary. It is important to replace aging or faulty circuit breakers with new ones that meet current safety standards. When selecting replacement circuit breakers, it is important to choose the correct type and size for the circuit. The breaker's amperage rating should match the circuit's rated capacity. The breaker's interrupting rating should be sufficient to handle the maximum fault current that could occur on the circuit. In addition to replacing faulty circuit breakers, it is also important to perform regular maintenance on the electrical panel. This should include inspecting the breakers for signs of wear or damage, tightening loose connections, and cleaning the panel to remove dust and debris. Circuit overloads occur when the current draw on an electrical circuit exceeds the circuit's rated capacity. Overloads can cause overheating, insulation breakdown, and equipment damage. Circuit breakers are designed to protect against overloads by tripping and interrupting the flow of current when the circuit's capacity is exceeded. However, if a circuit is consistently overloaded, the circuit breaker may not trip quickly enough to prevent damage. There are several factors that can contribute to circuit overloads. Firstly, adding too many devices to a single circuit can exceed the circuit's capacity. Secondly, using high-power devices on a circuit that is not designed to handle them can cause an overload. Thirdly, faulty wiring or equipment can cause excessive current draw. To prevent circuit overloads, it is important to distribute the load evenly across multiple circuits. Avoid plugging too many devices into a single outlet or extension cord. Use power strips with built-in circuit breakers to protect against overloads. If a circuit consistently overloads, consider upgrading the panel to increase capacity or adding additional circuits to distribute the load more evenly. It's also important to ensure that all electrical work is performed by qualified and licensed electricians who are familiar with local codes and regulations. Proper installation and maintenance are critical to ensuring the safety and reliability of the electrical system. Understanding voltage regulators, also known as automatic voltage regulators, is crucial for maintaining stable power supply and protecting sensitive electronic equipment. A voltage regulator is an electrical device designed to automatically maintain a constant voltage level. It stabilizes the voltage provided to electrical equipment, protecting it from voltage fluctuations and surges. These regulators are essential in areas where voltage levels are unstable or prone to variations, such as industrial facilities, commercial buildings, and even residential settings. There are several types of voltage regulators, each designed for specific applications and voltage levels. Firstly, ferrocent voltage regulators utilize a saturated transformer to maintain a stable output voltage. Secondly, tap-changing voltage regulators adjust the transformer tap position to regulate the output voltage. Thirdly, electronic voltage regulators use electronic components to regulate the output voltage. Fourthly, servo-mechanical voltage regulators utilize a servo motor to adjust the transformer tap position. When selecting a voltage regulator, it is important to consider several factors. Firstly, the input voltage range is the range of input voltages that the regulator can accept. Secondly, the output voltage is the desired output voltage that the regulator will maintain. Thirdly, the load capacity is the maximum amount of current that the regulator can supply. Fourthly, the regulation accuracy is the degree to which the regulator can maintain a constant output voltage. Fifthly, the response time is the speed at which the regulator can react to voltage fluctuations. Voltage regulators offer several benefits. Firstly, voltage stabilization maintains a stable voltage supply, preventing damage to equipment caused by over or under voltage conditions. Secondly, surge protection provides protection against voltage surges, protecting sensitive electronic devices from damage. Thirdly, power quality improvement reduces voltage fluctuations and harmonics, improving the overall power quality. Fourthly, energy savings optimizes voltage levels, reducing energy consumption and saving money. Regular electrical maintenance is vital for ensuring the safe and reliable operation of electrical systems. Regular maintenance can help prevent electrical hazards, equipment failures, and costly repairs. A comprehensive electrical maintenance program should include the following tasks. Firstly, visual inspections check for signs of damage, wear, or corrosion on electrical equipment. Secondly, thermal imaging identifies hotspots and potential problems using infrared cameras. Thirdly, insulation resistance testing measures the resistance of insulation materials to detect insulation breakdown. Fourthly, ground resistance testing measures the resistance of the grounding system to ensure proper grounding. Fifthly, circuit breaker testing verifies the proper operation of circuit breakers under overload conditions. Sixthly, voltage and current measurements monitor voltage and current levels to detect imbalances or overloads. Seventhly, cleaning removes dust, dirt, and debris from electrical equipment. Eighthly, tightening connections ensures secure connections and prevents loose connections. Ninthly, labeling ensures proper identification of electrical components and circuits. Tenthly, documentation maintains accurate records of all maintenance activities. It is recommended to establish a routine for checking electrical panels at regular intervals, such as monthly or quarterly. The frequency of inspections can depend on the age and condition of the electrical system, as well as the environmental conditions in the location. During the inspections, observe the condition of the wiring and connections within the panel. Look for signs of fraying, cracking, or corrosion. If any issues are found, consult a licensed electrician to address them. When dealing with electrical systems, safety should always be the top priority. When performing electrical work, it is essential to follow safety precautions to minimize the risk of electric shock, burns, and other injuries. Firstly, always to energize the circuit before working on it. Use a voltage tester to verify that the circuit is energized. Secondly, wear appropriate personal protective equipment such as safety glasses, rubber gloves, and insulated tools. Thirdly, follow lockout-tagout procedures to prevent accidental re-energization of the circuit. Fourthly, never work alone on electrical systems. Have someone nearby who can provide assistance in case of an emergency. Fifthly, avoid working in wet or damp conditions. Sixthly, use only approved and certified electrical equipment and materials. Seventhly, follow all applicable electrical codes and regulations. Eighthly, if you are not qualified to perform electrical work, hire a licensed electrician.